I'm Cuauhtli Campos, and I will present to you LightMeUp, a backprint illumination paper display with multi-stable visuals. Despite the drive to digitize learning, paper still holds a prominent role in educational settings. And this is the case even though computational devices have several advantages over paper. One such essential advantage is their ability to respond to the user actions. For example, a tap on a link reveals more information about the topic of interest. This is called dynamic visual feedback. However, it is widely accepted that the prolonged and incorrect usage of these digital devices can hinder educational achievements. This motivates us to try to find new ways of providing dynamic visual feedback on paper. And we want to achieve this with minimal involvement of digital technology. An interesting approach for this is the usage of filters which enable one to hide layers of printed information. For example, placing a red filter on top of an exercise book hides solutions from the reader, enabling them to study. In a similar way, several different artworks can be shown on the same sheet of paper. Backprint illumination paper display concept, also known as LightMeUp, is a concept where all information presented to the user is printed on a sheet of paper. Information printed on the front of the paper is visible as soon as viewed, whilst the information printed on the back of the paper becomes only visible once the paper is back-illuminated. In our setup, we used a tablet computer as a backlight illuminator, on which a sheet of paper was placed. This setup doesn't suffer of any of the problems I spoke about in the previous presentation, so perforation and movement are not necessary. Let's look at the demo. Here you can see the back and front side of a standard paper. On the back side, we printed colors, and on the front side, contours. As soon as the paper is back illuminated, the colors are revealed to the observer. So, what is actually happening in this setup is that the back printed inks act as a light filter, allowing only specific wavelengths of light to pass through to reach our eyes. So, this made us thinking if we could perhaps replicate this exercise book example where the filter was used to hide layers of information printed in a specific color. Perhaps we could achieve a similar effect through carefully combining ink and backlight color. To better understand the concept, let's consider RGB color model. This is this cube you see here on the left. You can observe that cyan, yellow, and magenta are located at the corners of the cube. If you ever looked under the hood of your printer, you might have also noticed that these are the inks used for printing. Our hypothesis goes that if we can assume multiplication blending between the backlight and the ink, then it should be possible to print the text in cyan, yellow, and magenta on the back side of the paper, and selectively reveal it using red, green, and blue backlight. Please follow now carefully. If I take cyan color and multiply it with red, black layer will be the result. If I take magenta color and multiply it with red, I'm gonna get red color. In the same way, if I take yellow color and multiply it with red, I'm gonna get red color. What this says is that even though we printed 3 lines of text, cyan, magenta, and yellow, and back illuminated with red color, we should only see text printed in cyan. In the same way, if we illuminate it with green, we should only see text printed in magenta. Another example is if we illuminate it with blue color, we should only see the text printed in yellow. Through this approach, we should be able to selectively choose 3 different layers of information. To make this work, we need to make sure the inks do not overlap over one another. We can do this via a dithering pattern. You can see an example of it on the image to the right. This is what happens. Obviously, the result is not perfect, but the approach shows potential. And this is the case because the inks and backlights we use are not perfect. They don't act as perfect filters and light sources. More scientifically, the emissivity of spectra of light sources and transmittance light spectra of ink and paper are not ideal. And it turns out that there is very little prior work that measures transmittance light spectra of commonly available papers and inks. So, in this research, we set out to measure it ourselves, with a goal to build a simulator that will be able to synthetically generate imagery based on optical characteristics of displayed elements. We also set out to explore what are the interesting use cases of such a displayed concept. In order to build a simulator, we need light spectra data of all components within our display system. The emissivity of the light source, the transmittance of the paper, the transmittance of the ink, and sensitivity of the detector. As you see, the spectral data is always a function of wavelength, so special equipment is required for measurement. And in this research, we use our special setup that consisted of a hyperspectral camera pointing at a cardboard box which had a diffuser at one end and a light source at the other. The hyperspectral camera enabled us to capture light spectra of a two-dimensional area in the range of 400 to 1000 nanometers, covering more than the full visible light spectra. In all measurements, we capture area of 600 times 600 pixels. For each sample, the measurements were repeated 5 times, and the results reported hereafter are the average. We measured emissivity spectra for 5 light sources. Here you can see data for 3: Barco Projector, Galaxy Tab S4, and iPad 3rd generation. Both tablets clearly show 3 different peaks in blue, green, and red spectra. However, if you observe black line of Barco Projector, this is not the case. The profile is more uniform across the whole spectra, and for this reason, we chose it as a light source for measuring transmittance light spectra of papers and inks. We also measured light transmittance spectra of 6 commonly available papers. The result showed that the transmittance spectra was not constant across all wavelengths of light. This outcome had to be considered in the simulator, so we were correct to include it into our model. We also showed that overall opacity of paper is linearly proportional to the grammage. The heavier the paper, the more opaque it is. Finally, we measured light transmittance spectra of 2 types of printers, laser and inkjet printer. Results showed that neither of the ink types follow the ideal filtering curve drawn in black. This is particularly the case for magenta inks, whereas the transmittance of yellow ink best fits the ideal curve. This is why in our prototypes we only use cyan and yellow, as these pairs perform significantly better than pairs including magenta. Finally, we have all the spectral data that should allow us to build a simulator that is capable of synthetically generating the imagery. The simulator allows users to experiment with different system configurations, varying detectors, inkscapes, printing patterns. This enables educators and content designers to design multi-stable interactive visuals before they print their designs and help them decide on optimal system configurations. In this work, we also wanted to explore interesting use cases for such a display concept. We started by designing interaction techniques for illuminating. First, we introduced a gesture-based method for switching between different backlight colors. We present their different illumination styles: full screen, spotlight, and chasing spotlight. Using these interaction techniques, we set out to build various prototypes. The first one is drawing aid. As you can see, the red color only reveals the contour of the bird. and the blue color reveals the inner part of the bird. In a similar way, anatomy book could show skeleton and muscular layers, and crossword puzzle could reveal hints with the spotlight illumination. Another example is the geography exercise book that uses only white light color to reveal information. However, white light illumination only allows one layer of information to be revealed. In our research, we have found that the proposed concept is viable using commonly available light sources, paper types, and inks, currently limited to 3 stable visuals. Future improvements in inks or printing methods should be pursued. It is possible to create synthetical images using the proposed simulator. This novel display concept opens up interesting opportunities for novel interactive paper application. For more specific questions, collaboration, and information, do not hesitate and get in touch with us.